All right, so if e to the x is its own derivative, then it stands to reason that e to the x is also its own integral. And that's what this rule says. The general antiderivative of the exponential function e to the u du is equal to e to the u plus c. So let's look at some examples of that. Switching over to the tablet. All right, first we have the integral from 0 to natural log 16 of e to the x over 4 dx. So I have my own Mitchell patented term that I call baby u substitution. And it has to do with when what you have for your inside function is not just x, but it is just a multiple of x. I'm going to write it out for you at least this once, but I do want to hopefully eventually get away from it. So I am going to let u equal x over 4, which of course is the same thing as 1/4 x. And that's going to make du be 1/4 dx. Now, of course, I don't want a 1/4 dx, I just want dx. So if I multiply both sides by 4, I get 4 du is equal to dx. All right, so writing this integral in terms of u, e to the x over 4 is going to become e to the u. Dx is going to become 4 du. And now I'm going to change my limits of integration. Remember how that works? So what you see in the original integral are x limits. And u is x over 4. So 0 is going to still be 0, but natural log 16 is going to be natural log 16 over 4. Now here's something cute we can do. By the power property of logarithms, 1/4 natural log 16 is natural log 16 to the power 1/4. And 16 to the 1/4 just happens to be 2. So this new integral, instead of going from x equals 0 to x equals natural log 16, it will go from u equals 0 to u equals natural log 2. All right, and by the rule we just learned, the integral of e to the u du is e to the u plus c. We don't need the plus c because this is a definite integral. All right, so that's going to leave us with 4 times e to the natural log 2 minus e to the 0. E to the natural log 2 is just 2. E to the 0 is 1. So this integral comes out to 4. Isn't that nice? All right, next. The integral of e to the negative 1 over x squared divided by x cubed dx. This is also a u substitution. It is not a baby u substitution, just a regular u substitution. Okay, so u is going to be negative 1 over x squared, which I am going to call negative x to the negative 2. By the power rule, the derivative of negative x to the negative 2 would be 2x to the negative 3. So with that x cubed in the denominator, we have the x to the negative 3. We don't have the 2, so let's divide that out. X to the negative 3 dx is going to get replaced with 1/2 du. So this integral in terms of u is going to be e to the negative 1 over x squared is going to become e to the u. Dx is going, I'm sorry, this whole thing here, dx over x cubed is going to get replaced with 1/2 du. So that's going to be 1/2 e to the u plus c, but it's not about u. 1/2 e, and I'm going to write this as negative 1 over x squared plus c. Woo-hoo. All right, and then finally, we have what's called an initial value problem. Hopefully you remember these from Calc 1. Basically, an initial value problem is just an integration problem. And it comes with what's called an initial condition, which is what you see here. That initial condition is going to allow us to specify the value of c, of the plus c. So we're going to start by finding the integral of e to the negative t times secant squared pi e to the negative t dt. This is another substitution. I'm going to let u equal pi e to the negative t, which is going to make du pi times the derivative of e to the negative t. The derivative of e to the negative t is e to the negative t times the derivative of negative t, which is negative 1. Don't forget the dt. Okay, so we don't need the negative 1 and we don't need the pi. So let's divide both sides by negative pi, which means that e to the negative t dt is going to get replaced with negative 1 over pi du. All right, so here's what we have. We have secant squared of pi e to the negative t is going to become secant squared u. And then e to the negative t dt is going to get replaced with negative 1 over pi du. All right, so this is a Calc 1 integral, isn't it? The integral of secant squared u du is tangent u. Okay, and it's not about u, it's about t this time. Okay, so this comes out to negative 1 over pi tangent of pi e to the negative t plus c. Now we're not quite done because remember this was an initial value problem and they gave me the value of y at natural log 4. Let's put a y here. Okay, so going over to the next slide, let me just copy that equation real quick. We have y equals negative 1 over pi tangent pi e to the negative t plus c. Okay, and our initial condition said that y at natural log 4 is equal to 2 over pi. So here's how I like to write that. On the one hand, y at natural log 4 is equal to 2 over pi. On the other hand, y at natural log 4, just plug natural log 4 into this function we have here, is equal to negative 1 over pi tangent of pi e to the negative natural log 4 plus c. And we have enough information here to solve for c. So we have 2 over pi is equal to negative 1 over pi times the tangent of pi. Now, what is e to the well, Yeah, what is e to the negative natural log 4? Remember, we had a property of logarithms. I referenced it once earlier in this video. Negative natural log x is equal to natural log 1 over x. That means that this thing is equal to natural log 1/4. So what we have there is e to the power natural log. Let me make this an arrow. It kind of looks like a negative sign. Okay. We have e to the natural log 1/4. What is e to the natural log 1/4? It's just 1/4, isn't it? So that thing inside the parentheses just simplifies down to pi over 4. What is the tangent of pi over 4? The tangent of pi over 4 is 1. So we have 2 over pi is equal to negative 1 over pi plus c. That must mean c is 3 over pi. All right, so let's write our final answer. Big therefore, y is equal to negative 1 over pi tangent pi times e to the negative t plus, not c, because we know what c is now, plus 3 over pi. And that's going to do it for that problem. Hi, everybody. We're continuing with section 7.3. So now we're ready to define the general exponential function a to the x for any numbers a and x, both greater than 0. The exponential function with base a is a to the x equals e to the power x natural log a. And I'm sorry, I misspoke a second ago. X does not have to be greater than 0, just a has to be greater than 0. So x, a greater than 0, and x can be any real number. All right, now I'm not going to actually do this. I just want to explain to you that this is how you can do it. So you may or may not remember, I think I've mentioned it, that up to this point, we have only proven the power rule for rational exponents. And you would have done that back in Calc 1. And so that's the reason that several of these properties that I've stated, I've had to restrict the exponent to be a rational number. It's because those properties depend on the power rule. Well, now, using this definition of a general exponential function, even though this is technically not an exponential function, this definition still works. For any x greater than 0, and for any real number n, you can define x to the n to be e to the power n times natural log x. And then if you differentiate this function, you will find that it does in fact come out to be n times x to the power n minus 1. All right, again, I'm not going to do it. I'm going to resist the urge. So again, for x greater than 0 and any real number n, the derivative with respect to x of x to the n is n times x to the power n minus 1. So what you've done throughout Calc 1. Only now we know that it works for any real number exponent. You do have to be a little careful if x is less than or equal to 0. This formula will still hold as long as the derivative, x to the n and x to the n minus 1 all exist. All right, so here's something kind of fun. You'll see a little bit of this in your homework. The number e can be defined as a limit. We've already defined it another way, but some calculus books actually define it this way and then prove, for example, that This number e is the number that makes natural log equal 1. All right, so we're doing it this way. The number e can be calculated as the limit as x approaches 0 of 1 plus x to the power 1 over x. So what I always tell students about limits, and hopefully you've heard this before, is that the very first thing you should try to do with the limit is plug in the number and see what kind of form you get. In this case, the base would be 1 plus 0, which is 1. And the exponent would be 1 over 0, which is undefined, but we treat it as infinity. So this limit has the form 1 to the power infinity, which is what we call an indeterminate form. It gives you absolutely no information about what the limit is. Okay, and I do want to explain a little bit about why is this limit equal to e. So I have sort of an outline of a proof here. So consider this function f of x equals the natural log of 1 plus x. On the one hand, the derivative of this function at x equals 0, you know how to differentiate this. It would be 1 over 1 plus x times the derivative of 1 plus x, which is 1. And then when you plug 0 into that function, you get 1. So on the one hand, doing it that way, the derivative of that function at x equals 0 is 1. On the other hand, recall from Calc 1 that the derivative of a function at x equals a is the limit as x approaches a of f of x minus f of a over x minus a. So for this function, and this is something you should think about for at least 30 seconds, that limit would be the limit as x approaches 0 of natural log 1 plus x minus natural log 1 divided by x minus 0, which of course simplifies down to natural log 1 plus x over x. So since we know from this second bullet that the derivative of this function at x equals 0 is 1, that means we know that this limit is 1 because we know that this limit is the derivative. So writing that limit a different way, you get that the limit as x approaches 0 of 1 over x times natural log 1 plus x is equal to 1. Using the power property of natural logarithms, take this 1 over x and go, that limit becomes limit as x approaches 0 of natural log 1 plus x to the power 1 over x. That limit equals 1. And then finally exponentiate both sides of that limit. And you get e to the power limit as x approaches 0, natural log 1 plus x to the power 1 over x is equal to e to the 1. I'm leaving out a couple of little details here. Basically, just push this limit inside the natural log. And then that e and that natural log will cancel each other out, and you'll just be left with the limit as x approaches 0 of 1 plus x to the power 1 over x equals e. All right, so next we can talk about the derivative of a to the u, the general exponential function. All right, and this comes directly from the definition of the general exponential function. Remember, a to the x is e to the power x times natural log a. So using that definition, it's very easy to see that this derivative formula is correct. The derivative with respect to x of a to the u would be a to the u times natural log a times du dx. So your pre-calc instructor, hopefully, I know I did, for those of you who took me for pre-calc, may have pointed out to you that in calculus, and this is surprising, e to the x is the simplest exponential function and natural log of x is the simplest logarithm. And now we're starting to see why, because the derivative of this general exponential function is a little more complicated. It's a little messier than the derivative of e to the u, right? You've got this extra factor natural log a that pops out. which you don't have with e to the u. I mean, you do technically, but ln of e is equal to 1, so you can ignore it. All right, and then your corresponding integration formula, the integral of a to the u du is equal to a to the u divided by natural log a plus c. All right, here we have some exponential functions, and you would have seen a picture like this in pre-calc. Those functions are decreasing if a is between 0 and 1, increasing if a is greater than 1. All right, and I'm not going to read this whole thing to you because you've heard this before.